my postdoc will teach you how to calculate the eigenvalue, eigenvector soon, next hour. All right. We have, how many eigenvalues we have here? Huh? How many eigenvalues of this defective matrix here? We have 2 by 2 matrix, right? This is 2 by 2 matrix. 2. Both of eigenvalues are 0. 2 0 eigenvalues. But these 2 0 values only share one eigenvector. Right. If 2 0 eigenvalues share one eigenvector, means defective matrix. Okay. What is the big deal of this? Right? That's the problem. We know why the eigenvalue and eigenvector are so important in the control methods. All right. Eigenvalue, here I will say that 0 0 eigenvector, only one eigenvector. In general, we have 2 by 2 matrix. We're supposed to have 2 eigenvalues and 2 eigenvectors. Now we have 2 eigenvalues. That's true. They are repeated, but we have only one eigenvector. This is we call defective matrix. So here I will explain a little bit more in the math. Mathematics are important. However, if you don't know the physical meaning, your mathematics doesn't mean anything. Now we know that rigid body motion has 0 eigenvalues. We know that now. Okay. Now another important equation here is we call measurement equations. Because sensor gives you the value. What does that mean, that value? We know that x1, x2, x1. What is x1 here? X1 here. What does that mean? This is displacement, right? What x2 here? This is velocity, right? So we have x1 displacement, we have x2 velocities. So you can have a device to measure displacement, or you can have a device to measure velocities, right? Agree? So if you have displacement measurement, then we call y equal to x1. Y is your measurement quantity, can be volts, can be amps. And x1 is your displacement. Now assume your measurement happen to be not volt, not amps. You can convert to become meters, become centimeters. So in control area, all measurement equations we call y equations. Now if you have a displacement measurement, then y equal to x1. You have velocity measurement, then y equal to x1 dot, that means x2. You have acceleration measurement, y equal to x1 double dot, x1 double dot, right? Then you have m equals f equal to ds. Then there's a d term. Now you got d here. Remember this d term, that's important. This d term is direct transmission term. Why we call direct transmission term? Because in F, if you have acceleration measurement, your maximum Y, in matter of fact, is to measure the force. It's your unit won't be meter, won't be meter per second. Your unit will be what? Time or pounds or kilogram and so on. Now, in the control design, these equations, matrix equation motion, we call state equations. State. Our states, x1 is state, x2 is another state. So in here we have two states. State means S-T-A-T-E. So in control area, we have two equations. One is a state equation called matrix equation motions. We have measurement equations. Sometimes some book name it as output equations. So in control design, we all talk about matrix equations because we always use only first order rather than the second order equations. We always talk about eigenvalues of the matrix. That's the control. All right. This is one simple differential equations. Let's look at this, the next one. We call this system. We have displacement, we also have a force, there's a mass, we have spring constant here. Then the equation of motion here, the second order equation of motion called Newton's law and Hooke's law is like this. mx1 double dot equal to minus kx1 plus f. This system, this spring system, the equation of motion is mx1 double dot equal to minus kx1 plus f. M must be larger than 0. K is larger or equal to 0. If k equals 0, it becomes rigid body motion. If k is not equal to 0, then it is we call vibrational motion. Now, don't forget this. N. I'm not joking. M larger than 0. Sooner or later.